Hello everyone! In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to examine quantum mechanics, the wave function, and the Copenhagen interpretation. Alright, so at this point you might ask yourself, what exactly happens when you make a measurement? Okay, and if you've been paying attention, you've probably spotted a problem with our interpretation of what is going on. Okay, so before I move any further, what I'm going to do is explain to you what is called the Copenhagen interpretation. So at this point, we are reasonably clearly into the philosophical interpretation of what this wave function is and what is happening with the wave function when you make a measurement. This is the most common interpretation. This is the interpretation that is most commonly taught in quantum mechanics. It is not perhaps my favorite for a variety of reasons, but it is one you need to understand pretty well in order to understand sort of the history of quantum mechanics, among other things. It is the classic interpretation of quantum mechanics. It's the interpretation that people will assume unless otherwise specified. And it has to do with what exactly we say happens when you make a measurement. And the problem you might have observed is that, well, if the probability of finding a particular particle is given by psi squared, then if you make a measurement and you actually find it in a particular location, you have just changed the wave function. And the reason you've just changed the wave function is if you find it right here, then you know it's there, which means the wave function squared has to be a spike exactly on that particular point. You found it there. You know exactly where it is. And so the probability of finding it there a split second later, for sufficiently small amounts of split, has to be exactly equal to 1. This process is known as wave function collapse. And what's happening formally is, according to the Copenhagen interpretation, the state of the system immediately becomes the eigenstate corresponding to the measured eigenvalue. So remember how I talked about this equation? The idea is, if you act with this operator to measure a value of, for example, the energy on this wave function, then this function is only going to be satisfied, this equation will only be satisfied by certain values of A, but those certain values of A will only satisfy this equation for certain eigenfunctions, that is, for certain values of the wave function itself. And so what happens is the moment you measure it, you get one of these as your energy, and this function becomes whatever it needs to satisfy this equation. That was sort of a loosey-goosey way of describing it, but this process is known as wave function collapse. So let me give you a more specific example. Take this wave function right here, and assume, or imagine for a second, that what is going to happen in a moment is we're going to measure the position. So the probability of finding the particle is going to be given by psi squared here, okay? And when we measure that position, I'm just going to note where we're going to find it. Notice it's not there. It's literally not there. There's no particle there, okay? There's no particle at all until the measurement is made, at which point the particle is found. So what happens? Well, according to the calculated probabilities, it's now found at position x, and so the wave function is now a spike. In particular, it's what is known as the Dirac delta function, right at the position it's measured. It's just a spike, okay, with 100% probability right here, and so is psi squared, okay? So is psi squared. But then, all right, what happens if you immediately measure its position again? Well, psi has not had time to evolve. And remember that the wave function will evolve according to Schrodinger's wave equation, and that will happen more or less immediately. But psi has not yet had sufficient time to evolve or to change or to be kind of wave-like. It's exactly where it was before. okay? And therefore, if you go and try to make that measurement again, it'll be exactly where you left it, okay? Psi is still where you left it, and the particle is still where you left it. But what if you wait and you let the wave function evolve according to Schrodinger's wave equation? So this spike eventually mellows out and sort of spreads out until it looks like a free particle again, but now centered on this measured position. Well, now if you measure the position, you will find it with the probability given by psi squared of this particular wave function, okay? And before the measurement, and this is really tricky, this is really quite tricky. Before the measurement, we say that the particle is in a superposition of the eigenstates psi. What this means for this particular example is, in order to describe it, we don't really want to say the particle is everywhere all at once. But to say, strictly speaking, what we say is the particle is in a superposition of the possible eigenstates it could be in once measured. And so we say it's sort of holding, the wave function is sort of holding all of the different states that particle could be found in at once. That's sort of a loose way of saying it. Yeah, this is sort of fundamentally the way the Copenhagen interpretation works. And you might ask, okay, so what constitutes a measurement, right? How do we know when the particle has been observed? And that is, in some ways the fiercest challenge of the Copenhagen interpretation. The obvious answer, it's observed when sort of a person observes it, seems deeply unsatisfying. And in fact, the answer, or the more sort of sophisticated answer is, well, it's observed when something interacts with it, which then is impacted, affected by it, or affects it, or interacts with it in a way where its properties depend, or that interaction depends on the properties of the wave function to begin with. So when does wave function collapse happen? It happens whenever there is a sufficient interaction to sort of require the state to make a decision. That's, again, loose language, but, this is sort of a weird thing that happens, which is the wave function immediately collapses once it has been measured into the state that satisfies this particular equation.